Imagine you are standing on the side of a steep, uneven mountain. You are completely blindfolded, and a heavy fog surrounds you. Your only goal is to find the lowest valley. Because you cannot see the landscape, you have to rely entirely on the feeling of the ground beneath your feet to figure out which way slopes downward. This graph translates that physical mountain into mathematical terms. We call this a loss curve. The curve shows the range of possible errors for a given model, and that red dot way up here on the right side represents our current guess. Sitting high on the slope means the model is making highly inaccurate predictions. It is important to clarify that the graph we are looking at is not the machine learning model itself. Notice that it maps error on the y-axis against a model parameter on the x-axis. What we are actually looking at is the underlying engine used to train the model. The entire objective of this training engine is to navigate that single red dot down to the absolute bottom of the curve, representing the minimum possible error. And it must accomplish this using only localized information from the slope beneath it. To make those movements downward, we use a specific update rule. Theta equals theta minus the learning rate multiplied by the gradient. Here, the Greek letter theta simply represents our current parameter weight, the exact coordinates of our foot on the mountain. The gradient is the slope of our current position. Since our dot is sitting on the right side of the curve, the line of the slope points upward. Mathematically, that makes the gradient a positive number. This is where the subtraction sign does its job. By subtracting that positive gradient from our current position, the math forces our parameter weight to move in the exact opposite direction of the upward slope. It pushes us downward. The strict arithmetic directly mimics the physical constraint. Stepping backward from the incline is the only way to find the valley. Knowing the direction isn't enough. We also need to know how far to step. That is controlled by the learning rate, which acts as a multiplier that determines the size of our stride. Let's see what happens if we get impatient. We will place our dot high on the left side of the curve, giving us a negative slope. Then we crank the learning rate up to a massive number. What happens when you subtract a negative gradient multiplied by a huge learning rate? Pause the video and calculate where the new position of theta will end up. Because the step is so large, it subtracts a massive negative value, which shoots our position rapidly forward in the positive direction. The dot completely skips across the valley and lands higher up on the opposite side. Impatience breaks the algorithm. If the step size is too large, the error diverges into chaos, getting worse with every single update. Speed must always be balanced against precision. When we reset to a properly tuned, moderate learning rate, we get a reliable slow walk. The algorithm executes a series of controlled jumps, smoothly tracking down the curve. Notice the built-in, self-correcting mechanical feature here. As the curve flattens out near the bottom, the slope shrinks. Even with a constant learning rate, multiplying by a shrinking slope naturally makes the subsequent steps smaller. Eventually, the gradient hits zero, and the model locks perfectly into place at the absolute minimum. This local process scales up immensely. In real machine learning applications like stochastic gradient descent, this exact mathematical loop navigates complex topographies stretching into millions of dimensions, with countless parameters independently hunting for their local valleys. Here is your final cheat sheet for the update rule. You take the current weight, and you subtract the step size multiplied by the slope. Now that we possess the engine to walk down the mountain, what kind of terrain are we actually navigating? Next time, we will map out how decision trees structure the landscape itself.